Today we are going to learn about optimizing data flow in ML pipelines. We will explore efficient strategies to enhance data processing, reduce processing time, and minimize resource consumption in ML projects.
Welcome to our session on optimizing data flow in machine learning pipelines. Efficient data processing is a cornerstone of successful machine learning projects. In today's video, we'll explore key strategies to streamline data movement and transformation, ultimately reducing processing time and conserving valuable resources. We'll cover understanding data flow bottlenecks, techniques for data partitioning, leveraging distributed computing frameworks, efficient data storage strategies, integrating data caching mechanisms, automating data validation processes, and monitoring and logging data operations. By the end of this video, you'll have a comprehensive understanding of how to implement these best practices in your ML pipelines for optimal performance. Before optimizing data flow, it's crucial to identify where bottlenecks occur. Bottlenecks can significantly impede the performance of your machine learning pipelines. They often arise at stages where data is transformed, transferred, or stored inefficiently. Understanding the root cause of these slowdowns is the first step towards optimization. Common bottlenecks include I/O operations, inefficient data transformations, and network latency. Employing tools like data profilers and monitoring systems can help in pinpointing these issues. For instance, using Apache Spark's UI, you can gain insights into stages of execution, identifying tasks that consume excessive time or resources. By highlighting these areas, you can prioritize which aspects of the pipeline need optimization. Real-world case studies show that addressing bottlenecks can lead to significant reductions in processing time and costs, making your ML projects more efficient and scalable.
Data partitioning is a powerful technique to optimize data flow within machine learning pipelines. By dividing large datasets into smaller, more manageable parts, you can improve both processing speed and resource utilization. Partitioning allows for parallel processing, which is essential when dealing with large volumes of data. There are several partitioning strategies, including range, hash, and list partitioning, each suited to different types of data and processing needs. For example, in Apache Spark, data can be partitioned based on keys, allowing for efficient shuffling and reducing data movement across the cluster. It's crucial to choose a partitioning strategy that aligns with your data's characteristics and processing requirements. Implementing best practices, such as ensuring partitions are balanced and not too small, can prevent resource wastage. By optimizing data partitioning, your pipelines will be more efficient, leading to faster data processing and reduced operational costs. Distributed computing frameworks, such as Apache Spark and Hadoop, play a pivotal role in optimizing data flow within ML pipelines. These frameworks enable the processing of large datasets across clusters of computers, facilitating parallel processing and significantly reducing computation time. Apache Spark, with its in-memory processing capabilities, offers tremendous speed advantages, especially for iterative algorithms common in machine learning. Hadoop, on the other hand, is well suited for batch processing and handling large-scale data storage. The choice of framework depends on the specific requirements of your ML project. Consider factors like data volume, processing speed, and the nature of the tasks. Leveraging these frameworks allows for the distribution of data and computations, enhancing scalability and performance. By using distributed computing effectively, you can optimize data flow, ensuring your ML pipelines are both efficient and capable of handling large-scale data processing tasks. Optimizing data storage is critical for enhancing the performance of machine learning pipelines. Efficient storage strategies ensure that data retrieval is fast and resource efficient. One of the primary considerations is choosing the right storage format. Formats like Parquet and ORC are optimized for analytics, providing efficient data compression and encoding schemes that speed up data retrieval. Additionally, employing data compression techniques can further reduce storage space and I/O operations, enhancing overall efficiency. It's also important to consider the impact of your storage strategy on data retrieval times. For instance, a case study involving a large e-commerce platform showed that switching to Parquet format reduced their storage costs by 30% and improved query performance by 50%. By focusing on efficient data storage strategies, you can significantly optimize data flow, reducing costs and improving the responsiveness of your ML pipelines. Data caching is an effective method to improve the efficiency of machine learning pipelines by reducing redundant computations. Caching involves storing frequently accessed data in a temporary storage layer, allowing for faster retrieval during repeated operations. This can significantly speed up iterative processes, such as model training and evaluation. There are various caching strategies, including in-memory caching and disk-based caching, each suited to different types of data and access patterns. Tools like Apache Spark's caching mechanisms make it easy to implement these strategies in your pipelines. For example, caching intermediate data in Spark can reduce the time taken for iterative tasks by avoiding repeated data loading and transformation. Successful integrations of data caching have resulted in improved performance and reduced processing times in numerous ML projects. By integrating data caching mechanisms, you can optimize data flow, enhancing the overall efficiency of your pipelines.
Automating data validation processes is essential for maintaining data quality and ensuring the smooth operation of ML pipelines. Data validation involves checking the accuracy and quality of data before it's used in processing, helping to prevent errors and inconsistencies. Automated validation tools, such as TensorFlow Data Validation and Great Expectations, offer robust solutions for validating large datasets efficiently. These tools can automatically detect anomalies, missing values, and data type mismatches, reducing the need for manual intervention and minimizing the risk of human error. Ensuring data quality through automation not only improves the reliability of your ML models but also enhances the efficiency of your pipelines by preventing costly errors and reprocessing. By implementing automated data validation processes, you can optimize data flow, ensuring that your ML pipelines operate smoothly and deliver accurate, reliable results.
Monitoring and logging data operations are crucial for optimizing data flow in ML pipelines. These practices provide real-time insights into the performance and efficiency of data processing stages, enabling quick detection and resolution of issues. Tools like Prometheus, Grafana, and ELK Stack are widely used for monitoring and logging, offering powerful capabilities for tracking metrics and visualizing data flow. By implementing robust monitoring and logging strategies, you can gain valuable insights into data bottlenecks, processing times, and resource utilization. This information is essential for identifying areas of improvement and implementing optimizations that enhance pipeline performance. Real-time error detection and alerts also help in minimizing downtime and ensuring that data processing continues smoothly. By prioritizing monitoring and logging, you can optimize data flow, ensuring that your ML pipelines are efficient, reliable, and capable of handling complex data processing tasks. Let's explore a real-world case study that demonstrates the optimization of an ML pipeline. In this case, a financial services company was facing challenges with their fraud detection model. The pipeline was experiencing significant delays due to data bottlenecks and inefficient processing stages. The company conducted a thorough analysis to identify the root causes of these issues. They discovered that data storage formats were not optimized, and there was a lack of effective caching mechanisms. To address these challenges, the company implemented several optimization strategies, including switching to Parquet format for data storage, integrating Apache Spark for distributed computing, and incorporating in-memory caching for frequently accessed data. These changes led to a remarkable 60% reduction in processing time and a 40% decrease in resource consumption. The improvements not only enhanced the efficiency of the pipeline but also increased the accuracy of the fraud detection model. This case study highlights the significant impact of optimizing data flow in ML pipelines and provides valuable lessons for other organizations facing similar challenges. In conclusion, optimizing data flow in machine learning pipelines is essential for enhancing performance and reducing resource consumption. We've explored various strategies, including identifying data bottlenecks, implementing data partitioning techniques, leveraging distributed computing frameworks, and employing efficient data storage and caching mechanisms. By automating data validation and prioritizing monitoring and logging, you can ensure your pipelines operate smoothly and deliver reliable results. The benefits of these optimizations are clear, with improved processing times, reduced costs, and increased model accuracy. We encourage you to apply these techniques to your ML projects and experience the transformative impact of optimized data flow. Thank you for joining us in this session, and we hope you've gained valuable insights to enhance your machine learning pipelines.